let's take a look at a sample problem to see examples of how we can calculate the intervals where a function has certain behaviors. So in this problem, I am defining f of x to be 3x squared plus 4x minus 7. And the question that I'm asking is over what interval is f increasing, and also over what interval is f concave up. Okay, so let's break this into two parts. So the first thing we'll do is we'll talk about f increasing. So if we don't remember, we'll grab our derivative behavior reference sheet. And so increasing, a function is increasing when its first derivative is positive. So figure out when the first derivative is positive. First of all, what's the first derivative of this function? Well, it's a simple polynomial, so it's going to be 6x plus 4. All right, so we want to know when is 6x plus 4 greater than 0? That's what positive means. All right, and so we're just going to be using solving an inequality just like we did in Algebra 1. If you asked your teacher, when are we going to use this? Your teacher might have said, during calculus. All right, so we subtract 4 from both sides. Works just like a normal equation. Remember the only rule, I don't know why I said 0 there. The only rule we have is that if we multiply or divide by a negative number, we've got to flip the inequality. That's the only thing we need to worry about. Okay, but 6 is a positive number, so we don't need to worry about that. So x is greater than negative 2/3. All right, so this is the interval. So it's the interval, all of the x values where x is greater than negative 2/3. That's the part of the graph where the function is increasing. And you might remember that we can write this using interval notation if we felt like it. So it's going to be an interval that starts at negative 2/3 and it goes upwards. So it goes up all the way to infinity. We always use parentheses when we are talking about infinity because infinity is never included in this interval because infinity isn't really a number. And when x is equal to negative 2/3, it's not part of this interval. So we want to use open parentheses for that as well. Okay, so that's how you would describe it if you wanted to use it in interval notation. If you use just normal inequality notation, you could just write it like that. Either might be okay. If you were doing a multiple choice question, you might see it in either form. Okay, and the other question is talking about where is f concave up? So what does that mean in terms of derivatives? Once again, I'll go to my reference sheet, and thank goodness I made this. So concave up, now we're talking about a second derivative that's positive. So what's the second derivative of this function? Well, to find the second derivative, we're just going to find the derivative of the first derivative. So the first derivative is 6x plus 4, and so the second derivative is going to be just 6. And so this looks a little weird. For what values of x is 6 greater than 0? Well, 6 greater than 0, this is a true statement all the time. This is a true statement no matter what x is. So what that basically means is it means that any value of x represents a part of this function where this function is concave up. So if we wanted to talk about the interval over which it's concave up, we could say negative infinity to positive infinity. We could write it like that. Another way we could write it is if we write a capital R with an extra line here. This is little special notation, which just means all of the real numbers. Okay, so why don't we just scoot over to Geogebra for a moment and just see if the answers that we came up with satisfy our intuition from looking at the graph. All right, so I will share the screen to Geogebra just like this. All right, and so what we've got here is the graph of 3x squared plus 4x minus 7. And we said this graph is increasing whenever x is greater than negative 2/3. So x greater than negative 2/3 means an x value from here and all the way over in this direction. And that's where our turning point is there. All right, so that is what that says. That's the problem that we solved algebraically, saying that everything above that turning point is where the function is increasing. And then we saw that it was concave up everywhere, which makes some sense. It's got this parabola shape facing upwards, so it's never going to be concave down, and there are no inflection points for this function. Okay, with more complicated functions, we'll see that it can get a little bit more complicated. We'll take a look at that in the next video. We'll take a look at another example function.